Good day, everyone. So we will start. So basics. First, we have a set. Alright, so you need to pay attention because this will go fast. And if you don't understand this, you'll just be confused. So we have a set A. And in our set, we have elements. So with our set, we created something called the Cartesian product. So in other words, an element in my set was just a random A is an A. Then we defined something called the Cartesian product of a set A with a set B. And this set had elements in which the first element was from A and the second element was from B. And these are ordered pairs. Everybody's okay so far? So we define a Cartesian product between A and B, and so this set would contain all the subsets of A and B. So A1, B1, A1, B2, and so on. Everybody's okay? So for example, so a relation just relates two items, A and B. Straightforward enough. A common relation is the less than relation. So normally we refer to a relation as R. So any R, so a relation R would be a subset, this is definition. So a relation R on a set A is a subset of A cross A. In other words, if my B is A, then I'd say it is on A. Everybody's okay? Nice. So a relation is a subset from a relation on A is a subset of A cross A. Everybody's okay? There are different ways we can write relations. So if I have my, let's just say I have this relation that I call R, and in my relation I have the element AB, and my set in which the relation was on was A, B, C. Then I know that this ordered pair AB, I can write a few things. I can write either the ordered pair AB is an element of the relation, yes? Everybody's okay with this? Or I can write A is related to B. Yes? Again, it is building up, so you need to understand. So if I have the less than relation, so the less than relation, which is the simple less than relation that we all know, anybody could give me an element in the less than relation. Let's just say 3 would be less than what? 5. Yes? So I could write the ordered pair 3, 5 is an element of the relation, which is what I wrote here. Or I could write it in this form, which is the relation is not R, the relation is less than, yes? Or I could actually write A related to B, which is 3 less than 5. And this is what you all know. You all follow? So that is our context. So now we go a little further. Now instead of having two elements being related to each other, what I want now is I want to introduce an ordered pair. So I have two elements, and I introduce a rule in which they interact with. And based on that rule, it gives me an output. So in other words, I have A cross A, and this gives me an element in A. So A cross A, let's just say an element in A would be, say, A and B, and this would give me some output in A. So it's a value. You all following? Now I'm going to define an operation. So let's just say this operation is addition, which you all know. So if we have AB with this operation, then this gives A plus B. This is addition. This is the addition operation. So in other words, we take an ordered pair, two elements, and we give a value. A plus B is a value, right? So addition 3, 5 gives you 8. Yes? I'm going a little bit further, right? Coming back to relations, so just going back to relations. If I have a relation, and instead of listing my elements in my relation, A1, B1, A2, B2, and so on, if it is an infinite relation, that would not be possible because you will never end. So what we do is we give a rule. So we say that here, this relation R could be N and N plus 3, where N is in Z, let's just say. Yes? So what this relation would do, it would associate this element N with N plus 3. So could somebody give me an element here? So if N is 1, what would this next element be? 4. Everybody's okay with this? So then we say, okay, we understand this. Now we can write actually R of N equals to N plus 3. Yes? Now we do some magic on a relation to get a function with respect to the domain and being one-to-one. And so what you would know, what you are accustomed to, is say f of x equals to x plus 3. Everybody's okay with this? Nice. So I just want to bring this back to binary operations. So just as I had f, my operation is plus, and I have my brackets here, and my element is really an ordered pair, so I can have, I won't use A and B, I'll just use 3 and I'll use 5, and this is the ordered pair, and this would give me 8. Everybody's okay? But we don't write it like this. So what we do, we just give the relation, let star be a relation such that A star B is equal to, and we give what the relation is. Let's just say 1 plus A plus B. And you have to say where A and B comes from. Everybody's okay? So what we've now done, we have set some basis or grounding for binary operations. So more or less, long story very short, a binary operation is a rule in which we take two elements. So a binary operation is a rule that associates with two elements a third. Remember, this is a value, so this is really one element. Everybody's okay? Nice. So once we understand that, again, that is basic stuff. You need not have known that to answer the questions, but I believe it's always good to have a grounding, right? So we understand what a binary operation is now. Where it comes from, sets, cross products, Cartesian products. Cartesian products. What we're going to do from here is we're going to tackle about four questions, and in binary operations, you will more or less be met with 4 standard questions. The first is it closed? The second is commutativity. The third is associativity. The fourth is identity element. And the fifth is inverse. We could throw in a little extra thing and ask about distributivity, which is on question 1. Everybody's okay? The important thing is to understand what they mean. Because once you understand what they mean, you can apply that to all the questions and it becomes ridiculously simple. It just becomes an exercise in writing. So I've chosen 4 good questions. 3 each question builds on itself, and you would see very small differences in the questions, and then we end with a table, and I have a bonus question. Good luck with the bonus question. So hopefully after you could attempt the bonus question on your own time. Alright, so we're going to deal with closure. Closure deals with a set. So closure deals with a set. There are 2 things in binary operations. The first is always a set, and the second is the binary operation, right? So for example, if I were to say I define A star B as A plus B over 3. Now this is incomplete. I have defined the operation, meaning A plus B over 3, but I need to know where A and B comes from. So if I were to say on Z, so in other words, my A and my B come from Z. First thing I want to know is closure. So if Z. Now the set is what is closed. So this is important. Do not say the binary operation is closed. The binary operation cannot be closed. It just is a rule. You're following? It's just, that's all it is. But it is the set that needs to be closed or could be or cannot be closed. So let's just say this is the room. And I were to lock the doors. And I were to come back tomorrow. Then I will see all of you all here tomorrow. And the elements in this room would have been humans, yes? But if I were to do the exact same thing, and I came back tomorrow and I saw a dog, a random dog, and a dog, I know a dog is not here, then I would know for sure that the room was open. Somehow a dog came in, yes? In other words, in my set there was something that was not there before. That is closure. So I take elements in Z. Z have negative numbers, 0 and positive numbers. So I want to ensure that my output, and this is my output, is also in Z. Now, is this expression, will this expression always be in Z? Anybody? No, right? And all we need is one counterexample. So for example, if A is 1 and B is 1, then 1 star 1 is 1 plus 1 over 3, which is 2 over 3, which is not in Z. Everybody's okay? So Z is not closed under star. Anybody has any questions with that? Now, if instead of the operation being on Z, if the operation was on R instead, would it be closed or would it not be closed? It would be closed, yes? Because we know if we have two real numbers, say A and B, and we add them, A plus B will be in R. And if we have A plus B in R and you divide by 3, then this will also be in R. Everybody's okay? That's more or less closure. So all of your part 1s in your question most likely will be a closure question. So with that in mind, we will go to question 1. Please note the binary operation kit or the PDF that we're working from is in the link in the description below. So feel free to download it before you start the questions. Nice. Right, so we are on question 1. We want to show that Z is closed, and we define our operation as A star B equals to 1 plus A plus B. So our goal is to show that this here is in Z. So we want to show, our goal is to show that A star B is in Z. Yes? But we know that A star B is actually this. So in other words, we want to show that A plus B, 1 plus A plus B is in Z. That is our goal. So we start. So proof. We need, now this is important. The first question, I would say, you need to pay the most attention for the first question, because the second question and the third and the fourth is more or less the exact same thing, but I would not go into as detailed explanation as I am going into the first, yes? It's exactly the same thing. So we need to first take two elements in Z, yes? So you have to have these things. You must let A and B be elements of Z. If the set is not Z, then you need to take it in the set, yes? And our goal is to get this to be in Z. Now we know that, what do we need again? We need 1, yes? We know that 1 is in Z also. Therefore, 1 plus A plus B is in Z. Why? Because Z is closed under addition, yes? Since, and you have to write this, right? You have to write this, and Z is closed under addition. Hence, remember this here is exactly A star B. Hence, A star B is in Z, and you must put this after. Now, this has to work for all. This must work for all A and B in Z. Therefore, Z, again the setter, Z is closed on the star. Anybody has any questions? Everybody's okay? Lovely. The second question that always comes is a question on commutativity. Commutativity simply means that the order of the elements does not matter. In other words, if I had my element A star B, that would be the same as B star A. And this has to work for all A and B in my set. So what do? We take two elements in Z again. You will always start with that. So let A and B be elements in Z. Now A star B equals to 1 plus A plus B. And we want to get this to look like B star A. So on the side, what does B star A look like? B star A looks like, before I go into this, I did not emphasize how you read this, right? But let me just go into how you read this. So coming back here, A star B reads as this, A plus 1 plus A plus B. Listen how I say this, right? So A star B is 1. We don't know where 1 comes from. We are not concerned about it. We just know 1 appears from somewhere, yes? Plus the first element plus the second element. You all follow? That is how you read it. So B star A would be what? 1. We don't know where it comes from, nor do we care. Plus the first element, which is B, plus the second element, which is A. Everybody's okay? So I want to get that. So I want to make this look like this. Now I know that this is actually equal to 1 plus B plus A. Why? Since addition is commutative, right? Since addition is commutative. And this here is exactly equal to B star A. So we conclude, which implies that A star B equal to B star A, and you have to have for all A, B element of Z. Straightforward enough, right? Good. So now we come with associativity. Associativity deals with 3 elements. You will always have 3 elements, and you want to show that the order of the brackets does not matter. So in general, I want to show for associativity that if I were to have A star B star C, and if I were to group A and B, that is the exact same thing as if I were to group A star B star C. Yes? This must happen for all A, B, and C in my set, which is Z. Now, generally, associativity involves a little bit more working than commutativity, because associativity uses 3 elements and commutativity just uses 2. So what we do in general, we start with one side of the associativity equation very loosely. So we start with this side, we simplify, and then we start with this side, we simplify, and we show that their simplified lines are equal. Yes? So what is my first line? Anybody knows my first line? Well done. Let A, B, and C be elements of my set. Now, A star B star C. This is equal to what? A star B. Just remember, brackets first, right? So brackets first. Where does 1 come from? I really don't care. 1 plus the first element plus the second element star C. Now I have to simplify this. So what this gives me, this here now, so this entire thing here, what is before the operation is my first element, yes? So this simplifies to 1. Where does 1 come from? I don't know. I do not know, I don't care. Plus the first element, which is 1 plus A plus B plus the second element, yes? Then you simplify it and you make it look nice. 1 plus 1 is 2. Plus A plus B plus C. And then we start with the second side. Also, we start with this side now. So A star, open brackets, B star C equals to this side first. So A is A star 1 plus the first element in this case is now B plus C. And this gives 1, we don't know where 1 comes from, plus the first element, which is A, plus the second element, which is B. This simplifies to 2 plus A plus B plus C, which is the same thing here, yes? So then the next line, you write that is equal to A star B star C. And then you conclude, please conclude, make it look nice. Therefore, hence, A star B star C equals to A star, sorry. Again, it would not matter, right? But I'm just using the same format, right? A star B star C. And then I must have for all. Well done. Therefore, hence, star is associative. Yes? As well as at the bottom here, please write therefore star is commutative. Thank you very much. So now we go for identity. Now, the general equation for the identity is E star A equals to A, which is equals to A star E. Now, let me just give some basic information about the identity, some examples so you understand where I'm coming from. So, the identity depends on the operation. For addition, the identity element is 0. So if I have an element 5, I know 5 plus 0 gives me back the element which is 5, yes? I know, 0 plus 5 would give me back 5. Yes? So generally we use the letter E for the identity. So for addition, the identity is 0. Yes? For multiplication, thank you very much. For multiplication, the identity is 1. We want an element such that, say E multiplied by some A gives me back that element A. I solve for E, so I get E is 1. Yes? Just to make sure it works, 9 by 1 gives me 9, and 1 by 9 gives me 9 as well. We are going a little bit into more specific definitions. So you have two identities, so you need to pay attention, right? So you have a left identity and you have a right identity. And if we have a left identity and a right identity and they're the same, then it's called D-identity. You're understanding? Because we don't know that the operation is commutative. So some operations we might use or we might encounter may not be commutative. So in that case, if you solve, this is the equation for the left identity. Why? Because the E is to the left of A. So this is left identity. And this here is for the E is to the right of the A. So this is for the right identity. Are you all following? So when we are solving to find the identity, we use any one of these equations. We use either E star A equals to A or A star E equals to A and solve. If we use this and we solve, we get a value for E. Now in this question, because our operation is commutative, it means that we will get the same solution for this. You all follow? So you need to state that as well. And therefore you conclude that whatever value we get for E is the identity. THE, the one as in unique. Yes? So that's it. So what you need to understand that this is your main equation that you will always use no matter whatever the question is, matrices, numbers, integers, division, it does not matter. Once you know this equation, life is beautiful. It's just to simply decode whatever that means and go ahead with it. So we can start. E is the, I'll say left identity if and only if E star A equals to A for all A. Now this has to work for all the elements, and it will not change, it cannot change. 0 is the identity for addition. 0 does not depend on the number. You all follow what's going on? 0 is 0. 10 plus 0, a million plus 0, 0 minus 0 will not change. So sometimes if we do get an equation in which we solve for the identity and we see the identity is in terms of A, then that would mean the identity is not unique, which means it cannot work as an identity. We'll get to it though, right? Yes. So if you prove that the operation is commutative, once you find the identity, you simply say since the operation is commutative, therefore E is the identity. No, you don't have to find it, you just make a statement. Yeah, so we'll do that now. So what you do is you decode this and you solve for E. What do we want? The identity, right? I know it's obvious, but it's the same thing. And when the question changes it up, sometimes you start to doubt yourself, right? We want E. E star A is 1. We don't know where 1 comes from. The first element plus the second element equals to A. We cancel. We get E to be negative 1. Everybody's okay? Lovely. Two things we need to do after we find the expression for the identity. We need to verify that this identity is actually in my set. Because sometimes you get an expression for the identity and it's not in the set. So we know negative 1 is in Z. Yes? Hence, E equals to negative 1 is a left identity and since star, remember star is commutative, E equals to 1 is the identity for star. Everybody's okay? Straightforward so far. Anybody has any questions? Yes. If it's not commutative, then you need to work it out. What's that? Okay, so a little higher up, if you are able to solve the second half, as in if you get a left identity and a right identity, it will be the same value. Right? So so it's either you solve both and you get the same value, or you solve one and you get a value and you cannot solve the next one. It will just be unsolvable. There's a proof for that. It's a simple proof, straightforward, but I don't want to go into that now. Right? So now after that, we're going to inverses. So a bit on notation. This means the inverse of whatever is inside here, yes? And inverses are operation specific. So if I'm in multiply, the inverse of 5, well, I'll get to that in a while, right? The equation that we need to solve for inverses would be an element star the inverse of the element. I'm using this to represent the inverse, yes? some people use B and then just say B is the inverse, right? It makes no difference. I'm just using this expression here. And this has to be equal to my identity element. Everybody's okay? And what we do is we decode this and then we solve for A inverse. More or less straightforward. That's all we're going to do. That's all we will ever do. Which brings the point that we can only speak about inverses if we have an identity. Because if we don't have an identity, then we won't have E, so we won't be able to solve. You're following? Good. So for multiplication, we want to solve, so this is the general form. So for multiplication, we want to solve an element A multiplied by, say, an element inverse is equal to the identity. But the identity in multiplication is 1, yes? So we solve this and we get the inverse of A is really 1 over A. This is for multiplication. So here now, so for multiplication, the inverse of 5 is 1 over 5. Yes? For addition, I want to solve an element with the operation, the inverse of the element is the identity. But the identity for addition is 0. So if I solve for this, I will get the inverse of A with respect to addition is negative A. Yes? So now when I solve for my random operation, I'm going to get some random expression. So the full expression for the inverse would be the inverse A by the inverse would give me the identity, will also give me the inverse of A by A. So again, as with the identity, we have two inverses. We have the left inverse and we have the right inverse. So this equation here, what would this be? Anybody could guess? Either the left or the right inverse. Which one? The right inverse, because the inverse element is to the right of the operation, yes? And this would be the left inverse, right? Because it's to the left of the operation. Everybody's okay so far? Good. And then, if you have a left inverse, or once you use whichever equation you use to solve, you say left inverse, since it's commutative, is equal to the right inverse, therefore it's called D inverse. And then the follow question from that is, if it has a left inverse and it has a right inverse, then it must be the same inverse. Yes? So I want to solve, so A inverse is the, I'll say what? Right, I'll use right instead. Right inverse of A if and only if. What happens? A star A inverse equals to E, which means if and only if, right? Please, if and only if means you can go both sides. A1 plus A inverse equals to E. But what is E? E is negative 1. And we solve. What do we want? We want A inverse. And A inverse is this. So I get A inverse is negative 2 minus A. So we need to solve for A inverse. Solving for A inverse gives this expression, which is negative of 2 plus A. Now, having found this expression, we need to ensure that this expression is also in my set. So I want to make sure that this here is in Z. So for A element of Z, we know we want to get this, right? So we want to argue for this. A plus 2 is in Z, since Z is closed under addition. And also, therefore, minus into 2 plus A would be in Z, since Z is closed under multiplication. So multiply by negative 1. So, just randomly, y'all, what is the inverse of negative 5? To work it out, anybody? What is the inverse of negative 5? It is not a fifth. We now work it out here. We're talking for this question. So, negative 5 is a. So this is negative of 2 plus a, which is 5, which is negative 7, right? Yeah. Right. What does that mean? That means that if I were to say 5 star negative 7, I should get what? I should get what? 5. I should get in my identity, which is minus 1. So I should get minus 1, yes? So let's work it out. This is what? 1. We don't know where 1 comes from, right? 1 magically comes. We plus the first element, which is 5, and we plus the second element, which is negative 7. Oh my God, look at this. Oh boy. You all follow? So our next example, since you all were so on point with that one, what is the inverse of negative 4? The inverse of negative 4 is negative, open brackets, 2 plus a, which is negative 4, which is negative of negative 2, which is 2, yes? Which means that 2 star negative 4 will give me back what? Negative 1. My identity is negative 1, yes? This is the first element plus this, this is 1, 1 comes out from nowhere, plus the first element, which is 2, plus the second element, which is negative 4. We get 3 minus 4, which is negative 1. Everybody's following? So if you understand what I'm saying so far, then there's no way you can get a question like this wrong. Because if you find an identity, you could always work the equation and get it out. If you find an inverse, you could always take two numbers and multiply and ensure you get back the identity. Everybody's okay? Nice. So I just want to mention this point with respect to inverses. We found the inverse for this question as the inverse of A is this, right? So I know we did it already, but just very quickly, what is the inverse of 2? It would be negative 2 plus 2, which is negative 4, yes? And that would mean that 2 star negative 4 should give me back the identity element. And the identity in this case was negative 1, which is 1 plus the first element plus the second element, which gives negative 1, yes? Now, what is the inverse of a half? Work this out. Could you all work this out? So it's negative into 2 plus a half, which is yes, but this is bad, right? Because this is not in Z. Even a half wasn't in Z, right? I just wanted to make that point to you, right? The formula will work, it will work for anything, but we still have to remember what our set is on. So it is in Z, so a half has no right being there. A half doesn't even have permission to go into that formula. Yes? So please be aware of these things, because these are where we can ask you trick questions. What is the inverse of a half? And then you'll just go and write it down. Whereas we would like a half is not in Z, therefore it doesn't have one inverse. You follow? I don't think that question would come, but that is just me playing around, you know. Right, so now we come to the last part of the question, which is distributive, which is a standard question to ask. Generally not asked that often, but basics for distributivity, I will go with multiplication and addition. So we know that multiplication distributes over addition. In other words, if I have normal multiply A plus B, what is this equal to? This is equal to A multiplied by B plus A multiplied by C. Everybody's okay? So how I look at it as whatever distributes, you get more of. So here is one multiplication sign, but here you have two multiplication signs. You all see it? So this is more multiplication sign. So multiplication distributes over addition. That's an easy way to learn it. So in this question said, does star distribute over normal addition? So in other words, I want to know if A star or random B plus C will give me what? A star B plus A star C. And this has to happen when? For oh, lovely. Y'all don't forget this, huh? So what do? I take this side, I do my associativity format. I take one side, I simplify. I take the next side, I simplify, and I see if they're equal. So now A star B plus C, this is equal to anybody? All at once? 1 plus A plus B plus C, yes? And we can leave that like that. Also, A star B plus A star C, I'll just put it at the bottom here. Well, no, this is equal to, this is 1 plus A plus B comes out from nowhere, right? The 1 comes out from nowhere plus A star C, 1 plus A plus C, which simplifies to 2 plus 2A plus B plus C, yes? And this is not equal to this. Therefore, star is, sorry. Okay, in fact, before I conclude, right? Generally what happens is when we show something is not something, we give a counterexample. So simply just come up with a couple of values just to give an example. So anybody could choose some random values for A, B, and C. I would choose, now this is important, I have learned this from experience, do not choose the identity element. So we do not want to choose -1, right? So we choose A equals to 1, B equals to, and random guess, C would be Brit. Right? So 1 star, come on man, 1 star 2 plus 3 is 1 star 5, which is 1 plus 1 plus 5, which is 7. And 1 star 2 plus 1 star 3 equals to 1 plus 1 plus 2 plus 1 plus 1 plus 3. This simplifies to 2 plus 2 is 4 plus 5, which is 9, and 9 is not equal to 7. Therefore, star does not distribute over addition. Everybody's okay? Anybody has any questions? Nice. For a minute or two, just try question 2 part A, just to show it's closed. Just one point I want to make. This is a big point. So when we go into generally year 2 abstract algebra, you'll meet something called groups. And a group is a set associated with a binary operation we generally call dot or star. And it's such that G is non-empty. This is important, right? G is non-empty. So G is not equal to the empty set. There's closure. It is associativity. It's associative. It's associative. There exists an identity, and we have inverses. So this here forms a group. So in other words, my operation star together with my set Z actually forms a group. You ever heard the word group mentioned before? No, that's fine. Now, because this question, because star was commutative, remember it was commutative, this is actually an abelian group. An abelian means commutative, right? So abelian or commutative group. Now, this is where abstract algebra really starts. So when you go into year 2 or further when you pursue mathematics on a higher level at the university, you will be introduced to group theory. And there's a course called, so we've created a study group course, which I have mentioned before. It's abstract study group, and it's a 8-session course. So for all those of you who might be interested in it, please send an email to abstractstudygroup@gmail.com and just request I would like to enroll in the next offering of the abstract study group session. The email address is in the link below in the description. Lovely. So that's 45 minutes, right? We want to ease up that time. We'll probably break down this question to about 20 minutes or so, half an hour maximum. Go on to question 3 and then come back to question 4, yes? Lovely. So I'm going to pick up the pace. So you probably have to write quickly. Where are we going? Alright, so we're on to question 2 now. Question 2, different binary operation. Now we are using circle instead. So it really doesn't matter what we call the binary operation. Circle, star, squiggly, asterisk, circle plus, circle multiply, it doesn't matter. So our first goal again is closure. So we want to show that this is in Z. So what we do is, so for part 1 closure, we take 2 elements. So we take an X and a Y in our set Z, and we want to show that this is in Z. Now, we know that Z is closed under multiplication, so X, Y will be in Z, which implies that X, Y will be in Z, and you justify Y since Z is closed under multiplication. And now, so now we know that we have X and Y in Z. Therefore, X plus Y minus XY will be in Z, and this will be because Z is closed under addition. So although it is subtraction, it's still addition. You understand why, right? Why? You plus and minus, right? But plus and minus is really the inverse of the element. Yes? So it's really elements and their inverses. You all follow? That's why there are just only 2 operations, addition and multiplication. The inverse of addition is subtraction, and the inverse of multiplication is division. Since Z is closed under addition, which implies that X circle Y is in Z, hence Z is closed under circle. Anybody else any questions? So now we go to commutativity. Exact same thing. We take two elements and we show the order of the element does not matter. So the first line is let A and B be element. Now it doesn't matter if we choose X or Y and A and B, right? It's alpha, beta, whatever it is, just do not choose values. Don't choose numbers. Don't say 1 and 2 and 2 and 3, yes? So let A and B be elements of Z. Now A circle B is the first element plus the second element minus the product of the first element with the second element. Again, so our goal is to get this to look like B circle A. So on the side somewhere we could write what B circle A. So this would be equal to B plus A minus AB, and we can interchange A and B. Why? Because addition is commutative, right? Since addition is commutative. And then now we interchange the A with the B by the multiply for multiplication minus BA, and this is since multiplication is commutative. You all following what's going on? Now, so this is actually B, sorry, it's circle we're using, right? If I get confused, just, it's circle, right? I tend to get, I may write star instead of circle because generally we just use star, but I didn't want to have all my questions with star, 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 right? So therefore A circle B equal to B circle A, and what do I need to have? For all, yes, for all A and B in the set, and the set is Z. Hence, circle is commutative. Anybody has any questions? Everybody's okay? More or less kind of straightforward by now? And this goes right through. Unions, intersection, it doesn't matter the operation. You just understand what you have to do, show that the order does not matter. A, B, B, A, it doesn't matter. Right, so now we're going to associativity. So generally, same format. So we would start instead, what do we need to do now? We need to take three elements. So we need to take a X, Y, and a third element, Z in Z. So now, so remember we want to just start with the order of the brackets and then show that it doesn't really matter. So X star Y, sorry, circle Z. And we want to show eventually that this will be the same when I bracket with, when I use brackets on Y and Z instead. So what I do, I use this and I simplify, and then I take the next side and I simplify and I show that they're equal. So what is this equal to? This is equal to my first element plus my second element, subtract the product of the first and the second. Yes? Now y'all don't get confused here, right? Look at this carefully. So we are simplifying this now because the expression is a bit more complicated. This is, what does this give? Take a minute and write it down. Literally take a minute and write it down. So this is the first element, which is this entire bracket here. So this is my first element plus So it's my first element, plus my second element, y, well in this case it's z, minus the product of the first by the second. So the product of the first by the second is x plus y minus xy by z. And then I simplify this as much as possible. So this simplifies to x plus y minus xy plus z minus xz minus yz plus xyz. And then I write this in some sort of order so it is easy to identify. So I write the terms with 3 first. So this gives x, y, z, and then I'll write the terms with 2, minus xy, minus xz, minus yz, and then I have the single terms, plus x plus y plus z. And then I want to go and do the second side. So I want to say also x circle y circle z. And again, you just need to make sure, take your time. This works out to x circle the first element, which is y, plus the second element, which in this case is z, minus the product of the first element, which is y, by the product by the second element. Yes? We simplified, so x circle this now is the first element plus the second element in this long thing here, minus the product of the first and the second. So minus the product of x by the second, which is y plus z minus yz. And this you simplify, so you get x plus y plus z minus yz minus xy minus xz plus xyz. And this is exactly the exact same thing there. You just group it. And we group it in the same term. We start with the 3's, and then we go to 2's, and then we go to 1's. So this is xyz plus, no sorry, it's minus xy minus xz minus yz plus x plus y plus z, and this here you have to have this line is equal to this, which is this. So this is equals to x circle y circle z. Therefore, and then you conclude x circle y circle z equals to x circle y circle z, and what's going here? What's going on here? Oh, I love it. X. You see the reason is students don't put it on it, they lose a mark each time they do it. Commutativity, associativity, closure. So that's 3 marks. Yeah, and then they come on the exam, yes, I did so well, and then they see the mark and they're like, I don't understand. Hence is associative. Everybody's okay? Anybody has any questions? Just take a minute and try to work out the identity. It would not take long. Just work the equation and then we'll go into it, right? the time we finish this question, it should be fairly apparent of the routine. And then at the end of this question, you'll see a little trick. And it'll open you all to, okay, I need to pay attention for a couple of things. And by the time we finish today, you're going to just love binary operations. So at least I hope so. I mean, not really much they could ask that's different. The only thing you can do is just change up the algebra of the question, which might make it a bit harder. But the idea is the same. What values y'all got for E? Anybody got any value? Y'all got 0? Yeah. So we go. They say what? The third part? Yeah. Now we're on to the identity. Standard format as before. E is the identity if and only if E star A equals to A for all A in Z. And this is the right or the left identity? This is the left, right? So I just forgot that there. And then we translate what this means. What does this mean? If and only if the first element plus the second element subtract the product of the first and the second equals to A. Yes? What do I want? I want E. Yes? So I solve for E. So E, open brackets, 1 minus A equals to 0. Now look at this here. Somebody could say, well, you know, from this we get E equals to 0, which is correct. Huh? Or we get 1 minus A equals to 0, which implies that A equals to 1, yes? Both are correct, right? But I'm not concerned about A. I just want E. You all follow? So therefore, and we know that E is that 0 is in Z. So we know that the identity is in my set. Therefore, and then so from that we can say since circle is commutative, E equals to 0 is the identity. Is the identity for circle in Z. Right, so now we come to inverses. So we are solving the standard equation for inverses. And that is A by A inverse equals to the identity, yes? So same statement. So the statement would be A inverse again. You can use B or you could use another letter if you want. I just write A inverse one time to represent A inverse. So A inverse is the inverse of A if and only if A inverse circle A equals to E. Which implies that the first element plus the second element minus the product equals to E, and E in this case is E is 0. Yes? Right, so E in this case is 0, so we want to solve for A inverse. So we want A inverse. Remember what we want, please don't forget what we want. We want A inverse. So A inverse is 1 minus A equals to negative A, which implies that A inverse is negative A over 1 minus A. A inverse is A over 1 over A minus 1. Yes? So, there are a few things we need to ensure. So the first thing we need to ensure is that this is in Z. Now, will this always be in Z? That is my question. No, right? So it will not always be in Z. So which values of A will be in Z? So if I want this to be in Z, what condition could I impose on this for this expression to always be in Z? So I heard A not equal to 1. So you get division by 0, which is good. Then I heard what? A is greater than 1. So if I were to say A is 6, would that work? So the inverse of 6 would be what? The inverse of 6 is 6 over, which is 6 over, but does that make sense? No, because this is not in Z, right? Remember, we are in Z. So that means which elements then will have an inverse? 0. How did you get 0? Just because you look at it and pop out? Yes. What we realize from numbers is that, wait, look at this. 5 is what? 5 over 1. And negative 5 is 5 over negative 1, right? So in other words, if my denominator is either plus or minus 1, then it gives me an integer. Yes. A inverse equals to A over 1 minus A minus 1 will be an integer when A minus 1 equals to plus or minus 1, which implies A minus 1 equals to plus 1, or A minus 1 equals to minus 1, which implies A equals to 2 or A equal to 0. Do you follow? Therefore, there are only two elements which will have inverses, and that they are 0 and 2. Therefore, only two elements will have inverses. They are 0 and 2. Their inverses are of the form, and you just put back the formula. Everybody's okay? So, in the previous question, all the elements have inverses, yes? I don't know if I mentioned that at the end of the question, but if I did not, that should have been written, right? In the last question, after I found the expression for A inverse, which is negative into A plus 2, I should have had, therefore all the elements have inverses. I really can't remember if I wrote it in or not. Did I write it in? No? No? Okay. So random question, will this form a group? Will this form a group? Is it closed? Is it associative? Does it have an identity? Does it have inverses? Inverses has to work for all. So because only two elements have inverses, it would not form a group. You all follow? So we're on question 3. So the first thing we want to do is we want to observe what the set is. So we are given a set E. And E is, anybody could say what E is without verbally expressing -2, -0, and so on? The set of even numbers, yes? Lovely. So in other words, what this says is I take two even numbers and they are related in this way. It's the product and we then divide by 2. So the first thing I want to do, I want to show closure, yes? What do I start with? So part 1 is closure. So what do I start with? Let say x and let x and right, so what do we start with? Let A and B be elements of my set E. Now, if A and B are elements of E, what does that mean for us? That A is even, yes? You understand? which means A could be written as 2K, where K is in Z. And B is 2P, where P is in Z. So I want to show that the product, or sorry, A circle plus B is even as well. Now, A circle plus B equals to, what is A? A is 2K and B is 2P, but A circle plus B is A over B over 2. Yes? Which simplifies to 2KP, which is even. Or you could write 2 by M, where M is KP and that is in Z. Yes? Because that's how it's defined, right? If it is in E, it's 2 by something. Hence, again, the set E is closed under the operation. And the operation is circle plus in this case. Anybody else any questions? So now we go on to commutativity. So again, for commutativity, we take two elements and we want to show that the order doesn't matter. So we can still take A and B be elements of E, and we want to show, on the side we want to show that A circle plus B equals to B circle plus A. Yes? Straightforward. Let A and B be in E. Now A circle plus B is our definition. A B over 2. Yes? But I want that to be, this here is A B on 2. I want it to look like B A on 2. Yes? But A B on 2 is really B A on 2. Since what? Multiplication is commutative. Yes? You're like, she's generating, right? Sorry. Therefore, A circle plus B equals to B circle plus A for all A and B in E. Hence, circle plus is commutative. So now we come to associative, which is 3 elements, and we want to show that the order of brackets does not matter. So in other words, we let A, B, and C be elements of E. We start with 1, so now A circle plus B circle plus C. And now this one is a bit different because it's so straightforward. In the previous 2 questions, we had to expand and simplify. But in this case, we are actually able to take one side and go to the next side. If you can't see it, then that's fine. You start with one side and you go to the next side. But this one is fairly straightforward. So A circle plus B is A B over 2. And this will be circle plus with C. Yes? And remember, this is just a term. So this gives my first term, which is this here, so A B over 2, by my second term over 2, which is C over 2, which is A B C over 4. Yes? And I can rearrange this into A by B, so A over 2 by BC over 2. You're following? And this here is A circle plus B circle plus C with the brackets like that. Hence, we've shown it is commutative. Associative. Therefore, A circle plus B circle plus C equals to A circle plus B circle plus C, in which the order of the brackets is different. And this happens for all A, B, and C element of E. Hence, circle plus is associative. Sorry about that there. Alright, so now we want to go with our identity element. Same equation that we'll solve all the time. Now, is it okay if I, for interest of time, forget the formal steps and just give the working so I could get an idea of what's going on? But in a question, you need to put all the formal steps, right? If you do not put the statements, I should say, you will lose marks, right? So for the identity equation would be the identity star any element is equal to the element itself, yes? In this case, what does this mean? Sorry, so in our question, it's really E circle plus A should be equal to A. But E circle plus A is E by A over 2 equals to A, which solves to get EA minus 2A equals to 0. E A into E minus 2 equals to 0, and this gives A equal to 0 or E equals to 2. Yes? Again, I don't want A, I want E. So E equals to 2 and E equals to 2 is in my set. So therefore, it is the identity. And then you have to say, since it is a, so formally before you would have set up the question, E is an identity if and only if you put the equation and then you work it out and then you get this. And then you would say, since it is commutative, therefore E equals to 0 is the identity. Everybody's okay? Again, we've done 2 full questions with full proper working. So this is just for to get the routine of it. But make sure, please, you do not want to lose marks for statements and questions like these. I know it is a bit tedious and why do I have to write all this, but you need to write all of this. If you did not have to write all of this, I would not have written all of this on the board for the last 2 hours. So now, after we've found E, we want to solve for A inverse. So inverses of elements. So the formula for the inverse of elements would be the inverse circle plus a normal element should give me back E. But from before, we know E is equal to 2, yes? So therefore, we have the inverse of the element by the element over 2 gives me back 2. Therefore, the inverse of A is 4 over A. Yes? So when we reach here, we need to ensure or to determine if this formula for the inverse of an element A will work for all my elements. So what are my elements? So if I were to say 4, so on the side, what is the inverse of 4? So the inverse of 4 is 4 over 4, which is 1, right? But 1 is not in E. So 1 is not in E. So obviously we can see that not all elements would have inverses, right? So which elements would have inverses? That is the question. So here's where you need to think. So take a minute and think about it. Find out which elements will have inverses. Anybody? So I want this here to be in here, yes? So A has to be, I'm dividing by 4, right? So if A is 4, then I'll get 1, and we know 1 is not there, right? If A is greater than 4, then I'm going to get a fraction. So A cannot be greater than 4. So A has to be less than 4. Could it be 3? The answer is no, right? Because you get 4 over 3, which is not here. So if A is 2, then I'm going to get 2. You all seen that? Could A be 0? No, because I have division by 0. Could A be negative 2? Yes. So 2 and negative 2 would be the only two elements that have inverses. You all follow? So then we just put a statement like that. The only two elements that will have inverses are 2 and negative 2. The inverse of an element A is of the form 4 over A. That's just general, right? So that is what I worked out here. Are you all feeling more comfortable? Could I see? You're more like a 100% question now, right? If you see a question, it's like the same thing, closure, commutativity, associativity, inverse, identity. Straightforward, right? Right, so now we've come to the last question, which is question 4. Now, if you realize this question is a bit different, we have a multiplication table. And at face value, this question has 4 elements, and which means we are dealing with a finite set. So our set here has A, B, C, and D. Now, with respect to closure, we want to ensure that our output is still in my set, yes? How do you read this table? This table reads row by column. So in other words, let's just randomly say C. This row, you go up to my operation, star, and you go down to D, let's just say D. And that gives the intersection between this row and this column, which is B. So now we know how to read a table. This was just on the side. We need to ensure that it is closed. Remember what closure says. At the start, we said a set is closed if we take 2 elements and we start 2 random elements, and my output, whatever my output is, so my output is actually this, is actually in my set, yes? But in this case, my set is S. So in other words, I want to see if, I should have really used X and Y just to show generality. So because we have A and B inside the table, right? So any set, any 2 elements that I take X or Y in my set, I want to show that that X binary operation Y is also in my set, yes? And remember, as I showed there, we read the table row by column, and my output is actually the entries in my table. So these things here are my output values, yes? Which means that if for some reason, if this were, I'm just editing, right? So if this D were I, randomly it were I, would the set be closed? No. Why? Because I is not in S. You all follow? Simple, straightforward. So if in addition to having this I here, if this D here were 25, would it be closed? The answer is no, right? Because 25 is not in here. If I change back this I to D, so I have D here, but I still have this 25, will it be closed? No. Lovely, you all understand. So that's the first part. You all understand how to show closure, yes? Perfect. The second part is commutativity. So what commutativity says, remember, if I have 2 elements, X star Y, that has to be the same as Y star X. what that translates to in a table graphically would be, let's just look at it, right? And I want to see if you all could come up with the answer without me telling you all. So if I have, let's just say A star B is which element? A star B is this element, right? And B star A is which element? A. So I would want to show that these two elements are the same if it's commutative, yes? A star C is which element? This element, yes? And C star A is this element, right? So I would have wanted to show that this element is kind of like this element, yes? A star D is what? Here. And D star A is here. So if it were commutative, then I would have kind of wanted to show that this here is this element, yes? Are we going down now? So B star A is here. So B star C now. So B star C is this element. And C star B is this element. So I want to have shown that these two are equal, right? Anybody kind of seen a pattern? If this is the main diagonal, then it would have made sense to show that it is symmetric about the main diagonal. You all see that? But this is not symmetric about the main diagonal. So it is not commutative. You all follow? So you just draw a line down the main diagonal. If this is equal to this, and this is equal to this, and this is equal to this, this is equal to this, this is equal to this, and this is equal to this, then it's commutative. You all follow? So you wouldn't go literally and do all that. You just look at them and you see it. And if it is symmetric about the main diagonal, then you simply say that. From the table above, we see our table is symmetrical along the main diagonal, therefore it is commutative. If it is not symmetric, which in this case it is not, what do? We give a counter example. That's what we need to do. So what is the counter example? So now commutativity, it is not commutative. So we just need one counter example. And from the table, we see that we're going to use this example. So C now, C star A is equal to D, but A star C is equal to A star C, which is B. And if you want, you can just emphasize it's not D. Yes? Hence, our operation is not commutative. Right, so now we come to identity elements. We go back with our main equation for the identity element, which is an element by the identity element gives me back the identity element, yes? Or the identity element by an element gives me back the element. So in other words, what I wanted, let's just say if A were the identity element, please watch how I'm doing this, right? If A were the identity element, then A star A should be what? A. If A was the identity element, then A star B should be B. If A was the identity element, then A star C would be C. If A was the identity element, then A star D should be D. So in other words, if A was the identity element, then this row would have been repeated here, yes? But it was not, so A is not the identity. So look in the table, and is there any row in which the top row is repeated? B. Yes? So what can we say? B is the identity element, yes? But wait, remember we have left identity and right identity. So this here tells us that B star A is A, and B star B is B, and B, right? Which means B is to the left, right? So B would have been the left identity, yes? So for the right identity, instead of having a row repeated, what would we have repeated? A column. Is there any column that is repeated? A, B, C, D? A, B, C, D. So yes, so in other words, B is the left as well as the right identity, therefore it is D identity. So the last part of the question, does our operation have any inverses? What is the main equation for the inverses? The inverses will be an element. By the inverse of the element should give me back what? E, the identity, yes? The identity in this case is what? B. So I want an element by some other element should give me back B. Everybody's okay? B is what? B is what? The output. Meaning that I search in my table for all my B's first. So I search in my table and where do I find B? I find B here, I find B here, I find B here, and I find B here. Any B's anywhere else? No. So, from these 4 B's that I have, I can get 4 equations. So for this first B, I get A star C is B. The second one I get B star B is B. The third one I get C star D is B. And the fourth I get D star A is B. Everybody's okay? Now, if we look at this, C would be the right identity of the right inverse of A. Y'all see that? C would be the right inverse of A, or A would be the left inverse of C. Y'all follow? This here, B would be the left inverse and the right inverse of B. So therefore, this here, so B is the only element that has an inverse. Y'all follow? The question says, any elements have inverses. So when we say have inverses, we mean the inverse, which means left and right. Yes? The left inverse of B is B and the right inverse of B is B because B times B is B. Yes? This here, D is the right inverse of C and C is the left inverse of D. So there's no left and right equality here. Likewise here, A is the right inverse of D because it's to the right, and D is the left inverse of A. You follow? So this only has one-sided inverse, one-sided inverse, one-sided inverse. This has both-sided inverse, which means it is D inverse. You follow? So the only element that has an inverse would be B, and that makes sense. E is the identity, and generally the identity is its own inverse. So one last thing to remember, please, if you pursuing higher maths and you are interested in the abstract study group, please send the email. I highly recommend sending the email so you can get access to the free course. Apart from that, enjoy the rest of the day and I will see you all tomorrow.